The date is March 14, 1945. A single Avo Lancaster bomber taxis onto a runway in Lincolnshire, England, sitting so low on its landing gear that ground crews wonder if the tires might blow before takeoff. Inside its belly hangs a bomb that weighs more than some fighter aircraft. 22,000 lbs of hardened steel and Torpex explosive. The pilot, squadron leader C.C. Calder, knows his aircraft is carrying a weapon that 5 American B-7 flying fortresses couldn't lift. Even if you chain them together, this isn't propaganda or national rivalry talking. It's pure mathematics, engineering reality, and a fundamental difference in how Britain and America approached the bomber war over Europe. The Lancaster wasn't just better at carrying heavy loads. It existed in a completely different category of payload capacity. When American bomber crews talked about their aircraft's capabilities, they measured bomb loads in terms of quantity and coverage. The B-17G, the most common variant flying over Germany in 1945, could carry a maximum of 8,000 lbs of bombs on short-range missions. Realistically, on deep penetration raids into Germany, that number dropped to around 4,000 to 6,000 because you needed fuel to get there and back. Do the math. 5 B-7s working together could theoretically deliver $20,000 to $30,000 of ordnance. But here's what the math doesn't tell you. Those bombs would be scattered across 5 separate aircraft, released from 5 different points in the sky, hitting 5 different impact zones spread across hundreds of feet. The Lancaster, in contrast, could put 22,000 pounds onto a single aim point. 1 aircraft, 1 bomb, 1 target. The implications of this capability reshaped what was possible in strategic bombing. There were structures in Nazi Germany that couldn't be destroyed by carpet bombing, not because the Allies lacked explosive power, but because they lacked concentration of force. Submarine pens with 23 ft thick reinforced concrete roofs. Viaducts built by Prussian engineers in the 1840s with stone are so massive they'd survived a century of weather and still carried heavy rail traffic. Underground factories carved into mountainsides. These targets laughed at conventional bombing. You could drop 1,500 Labada bombs on them and accomplish nothing but cratered fields and wasted aircrew lives. This is where the Lancaster's unique capability entered the war. It wasn't designed to do what 5 B-17s did. It was designed to do what 5 B-7s couldn't do even in theory. The aircraft could carry weapons that broke the rules of what aerial bombardment meant. And by March 1945, it was carrying the Grand Slam. A weapon so large that Barnes Wallis, its designer, had conceived it before the war started, but couldn't build it because no aircraft existed that could lift it. The Lancaster made the impossible possible, and in doing so, it changed the final months of the European war in ways that official histories often understate. Barnes Wallis didn't start with a bomb design. He started with a problem that conventional explosives couldn't solve. In 1939, while working at Weisser's Armstrong, Wallis became obsessed with a question that kept him awake at night. How do you destroy something that's built to survive direct hits? His answer turned bombing theory inside out. Instead of trying to blast through a target's defenses, he would bypass them entirely by attacking the ground beneath the structure. He called it the earthquake bomb concept, and it required rethinking everything the Air Forces thought they knew about explosive weapons. The theory was elegant but brutal. Drop a bomb from high enough altitude, ideally 40,000 ft, and let gravity and aerodynamics turn it into a supersonic projectile. The bomb wouldn't explode on impact. Instead, it would punch through soil, clay, and rock like a bullet through water, burrowing as deep as possible before detonation. When it finally exploded 90 to 100 ft underground, the shock wave would behave less like a conventional explosion and more like a localized earthquake. The ground would heave and ripple. Foundations would crack. Structures engineered to withstand surface explosions would collapse from underneath because their designers never imagined an attack vector coming from below. Wallis tested his theory on paper first using calculations that borrowed from seismology, mining engineering, and ballistics. The bomb would need to be massive, far heavier than anything currently in the Allied arsenal. It would need a specialized shape, long, streamlined with a hardened steel casing designed to survive impact forces that would shatter ordinary munitions. And critically, it would need to be filled with Torpex, a British explosive compound that was 50% more powerful than TNT and had already proven itself in naval mines and depth charges. By 1941, Wallace had his specifications written down. The bomb would weigh $22,000 lb, measure 26 ft long, and require an aircraft that didn't yet exist. The British Air Ministry looked at his proposal and shelved it. Not because the concept was flawed, Wallace's mathematics were sound, but because in 1941, no Allied bomber could carry a 22,000 weapon. The largest bombs in service weighed $2,000. Four-engine-heavy bombers like the Short Stirling and Handley Page Halifax were still in development. The idea of an earthquake bomb was theoretically fascinating but operationally impossible. So Wallace went back to his drafting table and designed a smaller version, the Tall Boy. At 12,000, it was still enormous by 1942 standards, but it was within the realm of possibility if you modified the right aircraft. The Tall Boy became operational in June 1944, and it proved Wallace's theory correct. Dropped on the Somme railway tunnel in France, a single Tall Boy penetrated 60 ft of earth and rock before exploding, collapsing the tunnel and trapping a German Panzer division that was racing toward the Normandy beaches. Now the Air Ministry was interested. If a 12,000 lb bomb could do that, what could a 22,000 lb bomb accomplish? By late 1944, Wallace finally had his aircraft, the Lancaster, and the manufacturing capacity to build the weapon he'd imagined 5 years earlier. The Grand Slam was no longer theoretical. It was real, and it was terrifying. The B-7 Flying Fortress wasn't a failure. It was a masterpiece of American engineering philosophy, but it was designed with a completely different mission profile in mind. And that design locked it into capabilities that couldn't be overcome, no matter how much engineers wanted to push the envelope. When Boeing's design team laid out the B-17 in the late 1930s, they were building an aircraft for precision daylight bombing at high altitude. The theory was simple. Fly above the effective range of most flak. Use the Norden bomb sight to hit specific industrial targets and rely on mass defensive firepower. 13 Browning 50 caliber machine guns to fight off interceptors. Everything about the B-7's design served that mission. Everything about its design also made it impossible to carry super-heavy ordnance. Start with the bomb bay. The B-7's internal weapons bay measured approximately 11 feet long and just over 3 ft wide at its maximum. It was split into two sections divided by a structural beam that supported the aircraft's wing. This wasn't a design flaw. It was a deliberate choice. That central beam carried massive structural loads, keeping the wings attached during high-G maneuvers and rough landings. You couldn't remove it without fundamentally weakening the airframe. The divided bomb bay worked perfectly for the B-7's intended payload. Racks of 500 lb or 1,000 lb general-purpose bombs neatly stacked and released in patterns. But it created a hard ceiling on what the aircraft could physically contain. The largest single weapon a B-7 could carry internally was the 2000 B bomb, and even that required removing some of the bomb racks. Then there's the weight problem. The B-17G had a maximum takeoff weight of 65,500 pounds. Subtract the airframe weight 365 empty, and you're left with 20,965 for fuel, crew, ammunition, and bombs. On a long-range mission to Berlin or beyond, the B-7 needed roughly 2,800 gallons of fuel, which weighs about 17,000 pounds. Add 10 crew members with their equipment, oxygen systems, ammunition for all those defensive guns, and suddenly your available bomb load shrinks dramatically. The theoretical maximum of 8,000 only existed on paper for short-range missions where you could sacrifice fuel. In actual combat operations over Germany in 1944 and 1945, most B-7s carried 4,000 to 6,000 of bombs because anything more meant you wouldn't make it home. American strategic bombing doctrine didn't see this as a limitation. It saw it as an optimal solution. The USAAF believed in mass formations of bombers saturating a target area with hundreds of smaller bombs. The theory was that precision meant putting enough explosives over a general target zone that something important would get hit. A single B-7 couldn't destroy a ball-bearing factory, but 300 B-7s dropping 200 tons of bombs could obliterate the entire industrial complex. This approach worked for area targets like cities, railroads, and factory districts. It failed completely against point targets like submarine pens, massive viaducts, or underground bunkers where you needed penetration depth and concentrated explosive force, not coverage area. The B-17 was never going to carry a grand slam. The bomb was 26 ft long, more than twice the length of the B-7's bomb bay. It weighed nearly 3 times the B-7's maximum bomb load and more than half the aircraft's total payload capacity, including fuel. You couldn't modify your way out of these constraints. The B made a calculated gamble in 1940 that bigger was better, and they were willing to sacrifice other capabilities to get there. When AVO's design team led by Roy Chadwick began working on what would become the Lancaster, they weren't trying to match the B-7. They were trying to outcarry it by a factor of 3. The aircraft that emerged was a 4-engine heavy bomber with one overriding priority: maximum bomb capacity with maximum flexibility. Every other consideration, defensive armament, crew comfort, operational range, came second to the question of how much destructive power you could hang under the wings and deliver to a target. The key innovation was the bomb bay itself. The Lancaster's internal weapons bay measured 33 feet long and ran uninterrupted from just behind the cockpit to well aft of the wings. No central dividing beam, no structural interruption, just an enormous cavern that could swallow weapons the rest of the world considered too large for aerial delivery. Standard configuration allowed for 14,000 pounds of bombs, which already exceeded the B-7's maximum. But Chadwick and his team knew that number was just the beginning. They designed the bomb bay doors to be removable and replaceable with bulged fairings that extended downward, creating even more internal volume. When you installed the bulged bay modification, the Lancaster could accommodate weapons up to 33 feet long and carry weights that shouldn't have been aerodynamically possible. The structural engineering required to make this work was extraordinary. The Lancaster's fuselage used a geodetic-inspired structure with massive load-bearing longerons running the length of the aircraft. The wings attached to a central structural node that distributed weight across multiple stress points, rather than concentrating it on a single beam. This meant the aircraft could handle asymmetric loads and extreme center of gravity shifts that would tear other bombers apart. When you hung a 22,000 lb Grand Slam under a Lancaster, the aircraft's center of gravity shifted dramatically aft and down. The landing gear compressed under the weight, but the airframe held because it was engineered from the start to handle these exact scenarios. Power was the other piece of the puzzle. The Lancasterist 4 Rolls-Royce Merlin engines, the same legendary power plants that made the Spitfire fighters so successful. In the Lancaster, they were Merlin Zaxxas, or FE, each producing 180 horsepower. Combined, those 4 engines generated 5,120 horsepower, enough to lift a maximum takeoff weight of 72,000 lb. When you loaded a Grand Slam, the Lancaster actually operated at weights exceeding 70,000 lb, pushing the absolute limits of what the engines and airframe could handle. Takeoff runs stretched longer. Climb rates dropped to barely 200 feet per minute, but the aircraft flew, and that's what mattered. The modifications for Grand Slam operations went beyond just the bomb bay. Engineers removed the mid-upper gun turret to save weight and reduce drag. They stripped out armor plating that protected the crew. Some missions even flew with reduced fuel loads, accepting shorter range in exchange for the ability to carry the massive bomb. These weren't compromises the Americans would have accepted. The USAF's doctrine emphasized crew survival and defensive capability, but the British were operating under different constraints in 1945. The war was nearly won, but there were still targets that conventional bombing couldn't touch. The Lancaster, with its bulged bomb bay, gave Bomber Command a capability that existed nowhere else in the Allied arsenal. The ability to deliver a weapon of unprecedented size and power to a single precise point. By March 1945, fewer than 30 Lancasters had been specially modified to carry the Grand Slam. They operated as part of 6th Infantine Squadron, the famous Dam Busters, flying missions that regular bomber crews never saw. The Bierfeld Viaduct had become a symbol of German engineering resilience and Allied frustration in equal measure. Built between 1845 and 1847, this massive railway bridge carried the main rail line between Hamm and Hanover across the Johannesbach Valley in northwest Germany. Its 23 stone arches, each 50 of thigh, had been designed by Prussian engineers who built structures to last centuries. By March 1945, the viaduct had survived 54 separate bombing raids. The RAF had thrown over 3,500 tons of conventional bombs at it. American B-17s and B-24s had added their own attempts. The surrounding fields were pockmarked with craters. Sections of track had been hit and repaired dozens of times. But the viaduct itself, those massive stone arches, remained standing, still carrying German military traffic toward the shrinking front lines. This wasn't just about one bridge. The Bierfeld Viaduct represented everything that was wrong with strategic bombing against hardened infrastructure. You could hit near it. You could hit around it. Butte actually destroying 19th century stonework built with 3-foot-thick arches required something conventional bombing couldn't deliver. Concentrated penetrating force at a single structural point. The viaduct's arches distributed weight so efficiently that even direct hits from 2,000 WWII bombs merely chipped the stone. The structure was too massive, too well engineered, too fundamentally solid to be destroyed by surface explosions. Squadron received the order on March 13, 1945. 1 Lancaster, 1 Grand Slam, 1 target. Squadron leader Cedar would pilot the modified Lancaster carrying the earthquake bomb. The mission profile was unusual even by bomber command standards. The Lancaster would fly alone, no formation, no fighter escort for most of the route. It would climb to 20,000 ft over the target, far higher than normal for precision bombing because the Grand Slam needed altitude to reach its terminal velocity. The bomb site would be the advanced Mark the 15th, and the bombing would be done visually in daylight. Everything about the mission violated standard doctrine, but standard doctrine had failed 54 times already. March 14th dawned with clear skies over Lincolnshire. Rare luck for a precision bombing mission. Called as Lancaster took off at Erin 9:45 hours, struggling into the air with its 22,000-pound payload, dragging the aircraft down. The climb to operational altitude took 45 minutes. The 4 Merlin engines screaming at maximum power to lift the overloaded bomber. By the time they crossed into German airspace, the Lancaster was alone in hostile sky, too heavy to maneuver aggressively if fighters appeared. But German fighter strength had collapsed by March 1945. Most of the Luftwaffe's remaining aircraft were grounded for lack of fuel. The Lancaster flew on unmolested. At 12:47 hours, the Bierfeld Viaduct came into view. Calder brought the Lancaster into its bombing run, holding steady at 20,000 ft while the bomb aimer lined up the shot. The Grand Slam hung in the open bomb bay, its stabilizing fins visible below the aircraft's belly. At 12:49 hours, the weapon released. For armament, nothing seemed to happen. The Grand Slam dropped away so quickly it almost looked like it simply vanished. Then came the wait. A Grand Slam falling from 20,000 ft takes roughly 40 seconds to impact. Could bank the Lancaster hard to get clear of the blast zone, not knowing exactly what to expect. No one had ever dropped one of these on a bridge before. The bomb struck 30 ft from the viaduct base, penetrating deep into the earth before detonation. The explosion, when it came, wasn't the spectacular fireball of conventional bombs. It was something different. A heaving, rippling shockwave that traveled through the ground itself. 2 of the massive stone arches collapsed immediately, their foundations shattered by underground forces they were never designed to withstand. A 200 ft section of the viaduct dropped into the valley below. What happened beneath the Bierfeld Viaduct in those milliseconds after impact reveals why the Grand Slam worked when thousands of tons of conventional bombs had failed. This wasn't just about explosive power. It was about physics, timing, and understanding how shock waves behave in different mediums. When a standard 1,000 lb bomb explodes on the surface, roughly 95% of its energy dissipates into the air. You get blast, heat, and fragmentation spreading outward in a sphere, but only a tiny fraction of that force actually penetrates into the ground. It's spectacular to watch, and it's effective against soft targets like buildings or railroad tracks. But against massive stone structures built on deep foundations, surface explosions are almost useless. Oh, the Grand Slam operated on entirely different principles. From the moment it left the Lancaster's bomb bay at 20,000 ft, aerodynamics and gravity turned it into a kinetic weapon before it ever detonated. The bomb's shape, a long streamlined teardrop with a hardened steel nose cone, was designed to minimize air resistance and maximize terminal velocity. By the time it reached ground level, the Grand Slam was traveling at approximately 750 mph, just under the speed of sound. That velocity combined with 22,000 lb of mass created kinetic energy measured in millions of foot-pounds. The bomb wasn't just falling, it was punching through the earth like a meteor. The hardened steel casing was critical here. Barnes-Wallace specified a one-piece forged steel body with walls thick enough to survive impact forces that would shatter cast iron or standard bomb casings. When the Grand Slam hit soil, clay, and rock at 750 Melit Tempu, the nose cone compressed slightly but held its shape, creating a self-excavating projectile that burrowed downward. The bomb's momentum carried it through layers of earth that would stop conventional weapons dead. Soil mechanics research conducted after the war showed that the Grand Slam typically penetrated between 90 and 130 ft depending on ground composition. In the Bierfeld case, geological surveys suggested penetration depth of approximately 95 ft before the fuse triggered detonation. Now the earthquake effect began when 9th 135 lbs of Torpex explosive detonated 95 ft underground. The blast had nowhere to go but through solid earth. Unlike air, which compresses easily and absorbs shock waves, soil and rock transmit seismic energy with brutal efficiency. The explosion created what seismologists call a wave, a ground-rolling shock wave that travels along the surface while simultaneously generating compression waves that move through the subsurface. This combination produced effects similar to an earthquake measuring between 4.0 and 4.5 on the RTER scale concentrated in a small area. The WWII stone arches built in the 1840s were engineered to handle vertical loads, the weight of locomotives and freight cars passing overhead. They could even handle lateral wind loads and minor ground settling, but they were never designed for vertical acceleration from below. When the seismic wave hit the WWII foundations, the stone structure experienced upward acceleration, followed by rapid downward motion as the ground heaved and dropped. The architrave to flex in ways their rigid stone construction couldn't accommodate. Mortar joints that had held for a century cracked. The carefully balanced arch geometry that had distributed loads for so long suddenly became a liability as different parts of the structure moved at different rates. The camoufle effect, the underground cavity created by the explosion, added another layer of destruction. The Grand Slam's detonation vaporized everything within about 40 ft off the blast center, creating a spherical void in the earth. When the shock wave passed, that cavity partially collapsed, creating secondary ground shifts that continued for several seconds after the initial blast. Foundations that hadn't failed immediately found themselves suddenly unsupported, hanging over newly formed voids. This is why witnesses reported the WWII didn't simply explode. It seemed to sag and crumble in stages as if the ground beneath it had turned liquid. The fundamental difference between American and British heavy bombing wasn't about which country built better aircraft. It was about two incompatible philosophies of how to win a war from the air. When you put 5 B-17s over a target versus one Lancaster carrying a Grand Slam, you're not just comparing payload numbers. You're comparing two different theories of destruction, two different approaches to risk and concentration of force, and two different answers to the question of what strategic bombing was supposed to accomplish. 5 B-7s on a typical 1945 mission would carry approximately 20,000 to 25,000 pounds of bombs combined, roughly equal to a single Grand Slam by weight. But those bombs would be distributed across 5 aircraft flying in formation, possibly spread across 300 to 500 ft of horizontal space. Each bombardier would aim independently using his Norden bomb sight, trying to hit the target, but knowing that bombing from 25,000 ft with any precision was more hope than certainty. Even with good crews and optimal conditions, circular error probable, the radius within which 50% of bombs would land was typically 1,000 ft or more. This meant your 5 B-7s were effectively carpet bombing a 4-mile circle, hoping the target was somewhere inside that zone. The distribution pattern matters enormously when you analyze actual destructive effect. Those 20,000 of bombs wouldn't be 20 individual 1,000-pounders. They'd likely be a mix, Some 500 lb general-purpose bombs, some 1,000-pounders, maybe a few incendiaries, depending on the target. Each bomb would detonate on or near the surface, creating its own crater and blast zone. Against soft targets like wooden buildings or railroad marshalling yards, this saturation approach worked beautifully. You'd obliterate everything in that quarter-mile circle, but against a hardened point target, a submarine pen, a viaduct, a reinforced bunker, you'd achieve scattered surface damage with minimal structural effect. It's the difference between throwing a handful of gravel at a stone wall versus swinging a sledgehammer at a single point. The Lancaster with a grand slam represented the sledgehammer option. One aircraft meant one aim point, and by 1945, specially trained crews in 617 Squadron were achieving circular error probables under 300 ft from 20,000 ft altitude. More importantly, all 22,000 lb of explosive force would impact at a single location and penetrate to depths where conventional bombs never reached. The destructive mechanism wasn't surface blast. It was subsurface shockwave and foundation collapse. You weren't trying to blow up the target from the outside. You were trying to make the earth beneath it earthquake and heave until the structure collapsed from below. Risk calculation was another dividing line between the approaches. 5 B-7s meant 50 aircrew members. If you lost one aircraft to flak or fighters, you'd lost 10 men. But the mission could continue with 4 aircraft. The American philosophy accepted higher risk by distributing it across more aircraft and crew, betting that formations of hundreds of bombers could saturate defenses through sheer numbers. The Lancaster Grand Slam mission put all the eggs in one basket. 6 or 7 crew members, 1 aircraft, 1 bomb, 1 chance. If flak or mechanical failure brought down that Lancaster, the entire mission failed and the irreplaceable Grand Slam was lost. But by March 1945, German air defenses had collapsed enough that single aircraft precision missions had become survivable, and the RAF accepted that risk in exchange for the capability to destroy targets that mass formations couldn't touch. Cost-effectiveness tells another part of the story. A Grand Slam cost approximately $4,000 to manufacture in 1945, expensive by British wartime standards, equivalent to several months' salary for a skilled worker. But compare that to the cost of organizing and flying hundreds of bomber sorties against targets that couldn't be destroyed by conventional means. The Burfeld viaduct had survived 54 attacks. How many aircraft? How many bombs? How many aircrew lives had been spent trying to knock it down before the Grand Slam succeeded in one mission? When you factor in operational costs, the earthquake bomb became cost-effective precisely because it could accomplish in one sort what might otherwise require dozens or never be achieved at all. The Grand Slam's operational career was brief. Only 41 were dropped between March and May 1945, but its influence on military technology echoed for decades. When the war ended, Allied intelligence teams fanned out across captured German territory, documenting bomb damage. And what they found at sites like Bierfeld, the Ansberg Viaduct, and the Valentine submarine pen fundamentally changed how military planners thought about hardened targets. The earthquake bomb concept proved that depth of penetration mattered more than surface explosive yield for certain target categories. That lesson didn't disappear when the Lancasters were retired. It migrated into Cold War weapons development and eventually into the precision-guided munitions that define modern air power. The United States Air Force, which had been skeptical of super-heavy bombs during the war, reversed course almost immediately afterward. In 1946, American engineers began studying the Grand Slam's design and the damage reports from its missions. The result was the T-12 Cloudmaker, a 43,600 lb American earthquake bomb that took the concept even further. The T-12 never saw combat. It was developed too late for World War II and never used in Korea. But its existence proved that American military doctrine had absorbed the lessons Britain demonstrated. You needed specialized weapons for specialized targets, and sometimes one massive penetrating bomb was worth more than 100 conventional ones. The bunker-busting weapons that became critical during the Cold War were direct descendants of Wallace's earthquake bombs. When NATO planners looked at hardened Soviet command bunkers and missile silos, they realized conventional iron bombs were useless. The Soviets were building facilities with 20 to 30 ft of reinforced concrete overhead, sometimes buried under additional layers of earth and rock. The only way to threaten these installations was with deep, penetrating weapons that could punch through the overhead protection or, like the Grand Slam, bypass it by attacking through the ground. The American BLU-109 bunker buster, introduced in the 1980s, used a hardened steel case and specialized fusing to penetrate concrete before detonation, exactly the approach Wallasey pioneered 40 years earlier. Modern precision-guided munitions took the concept to its logical conclusion by combining penetration capability with GPS guidance. The GBU-28, developed during the 1991 Gulf War specifically to attack Iraqi command bunkers, weighed 5,000 lbs and could penetrate over 20 ft of concrete or 100 ft of earth. The GBU-57 massive ordnance penetrator, deployed in 2011, weighs 30,000 lbs and is designed to destroy deeply buried facilities that no previous conventional weapon could reach. These weapons trace their lineage directly back to the Grand Slam. They're built around the same core principle that Barnes-Wallis proved in 1945. Make the weapon heavy enough, hard enough, and accurate enough, and you can destroy targets that were previously considered invulnerable. The Lancaster's unique capability also influenced post-war bomber design philosophy, particularly in Britain. The Avro Vulcan, one of Britain's V bombers that carried nuclear weapons during the Cold War, inherited